Welcome back. In week 2, we mastered operators and learned how to convert between data types in C#. Now in week 3, session 1, we'll go under the hood, explore how your C# code is compiled, how the computer's brain and memory work together, and what really happens when you read from the keyboard or write to the screen. Let's get started. Here's our roadmap for today. Introduction, why understanding hardware matters, C# compilation and execution steps. The central processing unit, or computer's brain, memory hierarchy, why not all storage is equal, memory management, stack versus heap. Endianness, how bytes are ordered, character encoding, from text to numbers, input-output communication, how your program talks to devices. Why does under the hood matter? Because your C# code doesn't run in a vacuum. Knowing how memory works lets you write faster programs and understand errors like stack overflow. Recognizing that input-output involves your CPU, memory, and devices helps you appreciate what happens when you call a simple method like readLine or WriteLine. Let's see what's really going on behind the scenes. When you write C# code, the compiler first translates it into an intermediate language, a universal assembly that isn't tied to any specific CPU. At runtime, the just-in-time compiler turns that intermediate code into native machine instructions your processor understands. Those instructions are then fetched and executed, reading and writing data from memory as needed. The CPU, or central processing unit, is the computer's brain. It follows a 4-step cycle for each instruction. Fetch the instruction from memory, decode what it means, execute it using units like the arithmetic logic unit, and write back any results to a register or memory. Registers are tiny, super-fast storage inside the CPU that hold the values you're actively working with. Not all storage is equal. At the very top are registers, just a few bytes, accessed in a nanosecond. Next comes the CPU cache, a few kilobytes to megabytes, still in single-digit nanoseconds. Then main memory, or RAM, which holds your program's code and data, but is tens of nanoseconds slower. Finally, disk or solid-state drive storage runs in milliseconds. Well-structured code keeps hot data closer to the CPU for speed. When your C# program runs, it uses two main areas of RAM, the stack and the heap. The stack manages local variables and method calls in a last-in, first-out fashion. Memory is freed automatically when a method ends. The heap stores objects you create with the new keyword, and the garbage collector later reclaims memory when those objects are no longer referenced. Consider this method, void my method. Here, the integer and references live on the stack. The actual string and object live on the heap under the hood. Endianness is how a multi-byte number is stored in memory. In little endian order, the most common on modern PCs, the least significant byte is at the lowest address. So the hex number 0x12345678 is stored as 78563412. On big endian machines it would be 12345678. Most of the time .NET handles this for you, but it matters when you deal with binary files or network protocols. How do we store text? In older ASCII, each character fits in 1 byte, but that only covers basic English. Unicode aims to represent every character in every language. In C#, each char is a 2-byte unit using UTF-16, so strings can hold virtually any international text. Understanding encoding is vital when you read or write text files across different systems. When your program calls console, readline, or file.writeAllText, it doesn't talk to the keyboard or disk directly. It asks the operating system, which uses a device driver to send commands to hardware registers. When the hardware finishes, it sends an interrupt signal to the CPU. The OS handles it, and your data makes its way back to your C# code. Now let's review the complete journey of your C# program, step by step. Source code. You write human-readable C# files in your editor. Compilation to intermediate language. The C# compiler transforms your code into Common Intermediate Language, or CIL, which is platform agnostic. Just-in-time compilation. When you run your application, the .NET Runtime's JIT compiler converts CIL into native machine instructions optimized for your specific processor. Instruction fetch and decode. The CPU fetches each machine instruction from memory, decodes what operation it represents, and prepares to execute. Execution. The arithmetic logic unit or other execution units perform the work, reading and writing data in registers. Memory access. If the instruction needs data not already in a register, the CPU accesses cache or main memory to load or store values. Peripheral interaction. When you perform input-output, the request goes through the operating system to device drivers, which communicate via hardware buses and interrupts. By understanding each of these stages, you gain insight into performance bottlenecks, like excessive heap allocations slowing garbage collection, or subtle bugs caused by JIT optimizations. It also explains why certain language features, such as async methods or value types, exist. They optimize how your code is translated and executed on real hardware. To reinforce that flow, here is a diagram linking every stage. Your editor leads to C# source files. Compiler outputs to intermediate language. Assemblies .del or .exe. .net runtime performs to JIT compilation. Native machine code is loaded into CPU registers and cache. CPU execution interacts with to stack and heap in RAM. OS kernel bridges to device drivers to keyboard, disk, network. In practice, when you press a key, the keyboard's controller raises an interrupt. The OS's keyboard driver reads the scan code and places it into a buffer. A console.readKey call in your program invokes a system call that retrieves that buffered character. When you write text console, WriteLine marshals your string into bytes, the OS writes them to the display driver, and the graphics card renders the text on your monitor. This end-to-end picture shows how high-level statements like readline and writeline traverse multiple abstraction layers, language, runtime, operating system, and hardware, before producing a visible result. Keeping this diagram in mind will help you trace issues and optimize your applications effectively. Remember these core ideas. The CPU fetches and executes your methods. Registers and cache hold your hottest data. Stack and heap division affects variable lifetime. Endianness controls byte order for multi-byte values. Interrupts and drivers underlie every read-write call. Understanding these helps you debug, optimize, and design more efficient programs. Let's see endianness in action. In your console project, write code that uses bit converter. Get bytes on a hex integer, prints the byte array, and observe the order. Run it and note whether the least significant byte comes first. That tells you your machine's endianness at work. That wraps up session 1 of week 3. Today you learned how C# code becomes machine code, how the CPU and memory cooperate, and how text and numbers are actually stored. For your next steps, experiment with memory allocation in small test programs and dive deeper into the garbage collector's behavior in C#. And that brings us to the end of today's session. We've traced your C# code from source files all the way through compilation, just-in-time translation, CPU execution, memory hierarchy, and input-output interaction. Armed with this understanding of what really happens under the hood, you're ready to write more efficient, reliable programs. In our next lecture, we'll shift focus to conditions, how to make your applications branch, loop, and react to different scenarios using if, else, switch, and more. See you there. Thank you for joining me today. See you next time.